Hello and welcome to My Security TV, our Tech and Sec Weekly. This is our Tuesday afternoon episode, and today we're going to look at Australia's sort of space and launch capabilities. And we've got a lineup here, and we've been looking at specifically rotating detonation engine for space launch. And this is a commercial project and obviously some academic research in the background as well. We've got Travis Reddy, the Chief Executive Officer for DefendTex, and then we've got Dr. Adrian Pudsey, who is the Responsive Access to Space Technical Lead with RMIT University, and then also Associate Professor Matthew Cleary, who's the Deputy Head Research of the School of Aerospace, Mechanical and Mechatronic Engineering with the University of Sydney. It's great to have the University of Sydney back on. We had them on a few weeks ago looking at their semiconductors research as well. Now, we're going to move into space, and I thought I'd just throw these up as a memory. Our last episodes for 2020 looked at Space 2.0, Industry Insights number 1 and number 2, where we had Lloyd Damp, CEO with Southern Launch, and James Powell from New Zealand, co-founder of Dawn Aerospace. And then we spoke to Peter Kinney, Head of Sales at Gilmore Space Technologies, and Stefan Moroni, Country Manager with MathsWorks. So you can check those episodes out. And they're on My Security TV, obviously. So this is a nice, I think this is our first space one that we've done for the year that I can recall anyway. We've done a lot of episodes, and this follows on some rotating detonation engine for space launch, a media release that came out. And we're going to be joined by, I'll introduce them as I bring them on. We've got Associate Professor Matthew Cleary, Deputy Head Research of the School of Aerospace, Mechanical and Mechatronic Engineering from the University of Sydney. Matthew, thanks for joining us.
Hi, Chris. Thanks for having me.
Very good. And together we've got Travis Reddy there on the right, Chief Executive Officer with DefendTex, and Dr. Adrian Pudsey, Responsive Access to Space Technical Lead, RMIT University. Adrian, thanks for joining us. So it's always, sometimes I always highlight people with a real job, Adrian and Matthew. Sometimes you just go add that full title there. I like, that's why I just like editor. Now I've got some slides to share, and let me just bring this over. So maybe we're going to start off with, beg your pardon, one second. So Travis, you're going to kick us off, and this is the actual image here. We're going to walk through some slide decks, but in fact, maybe Travis, let's just start us off with the project and DefendTex and where DefendTex has come from, and we'll dive into this.
Yeah, thanks. So DefendTex is a defence research and development organisation, around 6 years. Over that time, we've grown to about 86 odd staff, and our real success has come from our collaboration with the university sector. We currently employ around 130 researchers across 24 universities, and 2 of our good collaborators are here today in the form of RMIT and the University of Sydney. We've been fortunate in that the Department of Industry and Science has assisted us on this particular project through a CRCP, or a Collaborative Research Centre project. And a CRCP differs from a standard CRC in that it has to be industry driven. It has to result in a commercial outcome in a 3-year time frame. So a very small, discrete project that has to have both a technical challenge and some core science that needs to be done, as well as a commercial outcome that comes through it. When we looked at the kind of project that we wanted to put into, and this is our 3rd CRCP, previously we've been successful in developing a hydrocarbon fuel system for hypersonic flight and for 3D printed energetics, specifically a 3D printed solid rocket booster. But in this particular case, we were interested in the responsive access to space problem. How is it that we can get a payload into orbit in a very short time? And with the defence threats that we have running through our organisation, we're particularly interested in the geopolitical environment where our space-based assets may cease to operate in a short period of time and create strategic surprise or strategic opportunity for our adversaries. And how can we go about creating a sovereign capability to fill that gap? And in so doing, how can we bring the rest of the space industry along with us on that journey? And in particular, academia. They do a lot of really good space research, but they suffer from the problem of not being able to get that research into orbit in a cost-effective way. And if they can get it into orbit, they end up in an orbit they don't want to be in. So we're looking at those smaller payloads, being able to get them up quickly and in a very cost-effective method. The methodology behind that was, if we take a conventional system we can maybe tweak that and get a couple of percentage points gain, but we're ultimately going to get a conventional outcome. So we wanted to rethink the problem and come up with an unconventional approach to how we get into orbit. And that's where the concept of the rotating detonation engine came into play. And I'll probably hand over to Adrian at this point to tell you about what a rotating detonation engine actually is.
Because I knew straight away. Maybe just a quick question. Exactly. It's like, okay, the DefendTex, how long have you guys been around?
This is year number 6.
Year number 6. Okay. And I suppose I take it there's links back there to defence. Where was the sort of the premise of DefendTex came from? Because it sounds like you've kind of growing and you've got a lot of projects on already. What was your premise?
So the premise here, being an ex-defence member myself, was all around asymmetric warfare, and that's the area we want to concentrate in. As you'll be well aware, Australia has a very small military force. We have a technological edge, and our potential adversaries outnumber us significantly and outspend us in some cases. So we're looking at how we can use technology to generate asymmetric combat power. And we've achieved that through a range of different projects, such as loitering munitions, so small low-cost drones that fire out of a grenade launcher, to trusted autonomous systems, so there's a very large number of projects.
Exactly.
I want to keep it in the space context of what we're talking now, without drifting into the defence stuff too much. But we got our start back in 2016 through a process called Army Innovation Day, where at the time Major General Kath Toohey was running Army Innovation Day, which was an opportunity for companies to bring new ideas to Army, kind of like a Shark Tank environment. We pitched that idea of the Drone 40, and that was taken up by Army at the time. Some seed money was given, we've developed it through, and now it's in service with the UK Army. It's also in the US DoD. So it's been a success story. And we hope that the detonation engine and our space work will be a similar success story.
Yeah, I've definitely seen that links, and we mentioned Lloyd there, former defence as well. So, you know, sort of that link between defence capability building, sovereignty, that's the link between our interviews today, is that keyword of sovereignty from Macquarie's data centre in government, in Canberra for government. And we're trying to build that here. And so Australia is trying to build a sovereign launch capability, correct?
Yeah, look, I think the Australian government's message has been very clear, that they've identified a number of key strategic priorities where they want sovereign capability. Defence is one of them, and space is another. The raising of the Australian Space Agency, I guess, is a testament to the seriousness that they're assigning to that. The recent inclusion of space is one of the critical manufacturing components in the in the manufacturing modernisation initiative that they're running now. I think there's $130 million available to assist manufacturing in space. It is a good indication of the seriousness that the government seems to have applied to the sector at last. Yep,
and I mentioned this Friday, this Friday, we're speaking to the Advanced Manufacturing Growth Centre in Adelaide as well. So many projects, but there's quite a number there with space related. So let's move through. Adrian, are you going to walk us through the slide deck?
Yeah, if you could just bring up the first slide, please.
Yeah, let's see what we've got. What I'll do is I'll make it larger, and let me just work this out, and then we should be able to. Just one moment. That's it. Let me just get rid of that. Okay, so talk us through the rotating detonation engine. It's awesome.
Sure. So conventional engines, and probably most people's, I guess, experience of combustion is a process called deflagration. And so this is it can be rapid, but it's a subsonic process. It's been around for, it's really the basis of pretty much every combustion engine that we have today. Rocket engines, gas turbine engines, piston engines, everything that you can think of that's in service is based around this deflagration process. It turns out, however, that under certain circumstances, certain conditions, that this slow combustion process can transition into something called a detonation wave. And that detonation process is much faster, and basically the combustion wave will travel through the mixture at very high speeds, in excess of 2.5 kilometers per second. And what we can get from this is a much greater extraction of energy and also work out of the products, sorry, of the fuel. And probably one of the most well-known concepts that use this is a pulsed detonation engine. It's been around for a while. And in a PDE, it's basically a really long tube. You fill that full of fuel and oxidizer and ignite it, and it will rapidly detonate and send some thrust out of the back for a very short time. And then you have the issue of refilling that with more fuel and oxidizer and firing it again. So it's not a very efficient process. You're only getting a very short time. So one way to fix that is the rotating detonation engine, as we have up there. And the reason it's better is because it's continuous. And if you look at that image, which is actually one of our, a representative of one of our 3D printed engines that we will be testing soon, you'll see that basically it's an annulus or a ring-shaped combustor. You should be able to see that there, and there's also that lower image. So it's a ring-shaped combustor. You have an outer and an inner body, and all the magic happens in the gap between them. So at one end we have an ejector ring, very, very similar to a conventional rocket. Then there's the combustor, and then on the far left is a nozzle, which again is fairly standard in a rocket engine. And basically the way that it works is if you inject fuel and oxidizer at exactly the right proportions in the right way, if the dimensions are just about right, then a detonation will actually travel around that ring continuously as long as you can feed it with fuel. So that's the basic principle. You can use this for other propulsion systems, so ramjet, high-speed flight. You can use it for gas turbine engines, are also something that's being looked into for flight and for ground power generation. So there's a lot of applications there. And I think the key point for us is that it's a next generation technology. It really is, it's a leap ahead over conventional rockets. And as Travis said before, in conventional sense, you know, we're always looking for this 1 or 2%, maybe 3% gain at great cost. What the RDE gives us is possibly 10, 15 or higher percentage gain in performance and efficiency, which is significant. Other benefits include the high power density, so you can pack these engines into a very small space as compared to physically, as compared to normal rockets. And also the pressure feed requirements are a lot less. So we can potentially do away with big heavy turbo pumps and either run much smaller turbo pumps or possibly even not have them at all. So there's a lot of advantages in the engine design, and that's really why I guess we're looking at this as the next generation.
There's a couple of questions. One is you're 3D printing this, advanced manufacturing?
That's right. So our first engine that you'll probably see in the picture next was conventionally manufactured, and we've now moved to advanced manufacturing with 3D printing, and our next engine is fully 3D printed.
And has that adapted the design as well, the fact that you can now print this off, and I take it you print it as one, or do you print still putting it into components?
At this stage it's components, but in the end we hope to print as a single piece. Certainly it's made a big change to our design. We can do things that are impossible to do with conventional manufacturing.
And the other one was, how much control over the detonation do you have, both the power but also the duration of that detonation?
So in terms of the power, you can throttle these. The stability of the detonation is certainly one of the issues that need to be overcome. But you can throttle them up, and you end up with more detonation waves. So the more fuel and oxidizer you pump in, the more waves you can produce and more thrust. In terms of the duration, we're at fairly short duration at the moment because one of the other major issues is the heat. So these engines get very hot very quickly, and if you don't actively cool them, you've probably got 1, maybe 2 seconds before they start disintegrating. So that's one aspect that we're looking at the moment.
Cool. Okay, next slide. So this is it in operation?
Yep, I'll probably hand this
Yeah, that's right. So as part of this this process, we've got up here a ground test facility for the rotating detonation engine. They're only one of its kind in the country. There's only a handful of them in the world. And this particular facility, I think, is a testament to the way that the project has been run and the success that we've achieved. in that it's a true industry university collaboration. So the facility itself is located on our premises. It's very difficult to build these kind of facilities within a university, just based on the density of students and the risk management policies that they have in place.
Yeah, I get it.
Staffed here by RMIT staff in conjunction with some DefendTex staff, and those staff run hand in hand. So for all intents and purposes, the RMIT research team is here on a daily basis, running engine test after engine test after engine test. Fully instrumented, as I say, supporting our additive manufacturing components of the engine. And what it's been allowing us to do is to build up expertise, not only in the design and fabrication of the engine, but in the way those engine tests are conducted, the links back to the work that we did in hypersonics, and the ability to bring those researchers through. One of the issues you have in research is you might do a 3-year postdoc, and then after that, you need to go off and find something else to do so that you can keep that expertise. But having these follow-on projects that are following a logical course allows those researchers to build those skills, apply them in a practical way, and then continue that journey through, hopefully all the way through to a TRL-9 system that reaches orbit. And
this is linked to another project as well, is it? Is this, and maybe where did this research come from? Is this from an individual researcher, or was it sort of industry requested or defence requested?
So it all started with a journey into hypersonics back in 2016, where we were looking. Australia has a very rich history in hypersonic flight through the HiFi program. Indeed, we're one of the handful of countries that have achieved hypersonic flight. Just as within space flight, I think we were the 7th country in the world to launch a satellite, the only 3rd country in the world to launch a satellite from our own territory. So Australia has a very proud history of being able to take early technology. So we're looking at hypersonics and trying to work out how we could do it better, and that's where the concept of a hydrocarbon fuel system for hypersonic flight came to be. Because most hypersonic flight is done with hydrogen. It's not the most efficient way to do it, but it's the simplest way to do it because you can model it very easily. We'll hear about modeling in a moment. So we want to take that to the next level. And through that process, we learn a lot about the combustion issues, a lot about the heat management. And then we started thinking about were there other ways to achieve hypersonic flight, that is, flight greater than the speed of Mach 5. Typically, it's done with a scramjet or a boost glide environment. You send something up high into the atmosphere and let it glide down and pick up speed. But again, if we want a different outcome, we need to think about the problem differently. So we started looking at alternative propulsion methods that may enable us to achieve that hypersonic flight. And that's where the concept of the RDE was born. We didn't invent the RDE, but we started to rethink the way to manufacture it, rethink the way to test it, and more importantly, rethink the way to use it. And that's
so this technically could be launched, I say, on a supersonic plane side of thing, and then fire and detonate and give you hypersonic. Correct. Right, got it. Okay, so it's not necessarily the base of a rocket for a rocket to launch off, but it could be used for that as well.
Yeah, look, it's an engine. An engine can be used for many things. It can be used to go horizontally, it can be used to go vertically, it can be used to produce power. It has very different modes that it can be utilised in. Being a defence company, we're obviously interested in all modes of propulsion.
Yeah, and how much control would you have over its size? Does it have to be a certain size, or you could not miniaturize it, but you could bring it down to quite a small size?
Engines at the moment go all the way down to 100 millimetre, so quite a small engine. We haven't gone below that yet, but the theory scales. Talk to the scaling.
Sure, there is a lower limit to the size for technical reasons associated with the detonation process, and of course it depends on what fuel you use and what oxidizer you use. In some cases, you're limited to very large sizes, so there is a size limit. But
at 100, it obviously has utility.
Yeah, I'm thinking of like the drone or unmanned type system. Okay, well, look, I'll bring up this one. This is probably the most exciting one. They're all good, but let me just bring this one up. Okay, talk us through this one. This is it at detonation, obviously.
Yeah, this one's just here as a pretty picture. So all the orange one, all the orange pictures there you see are at the startup process right at the beginning with a high-speed camera. So that very quickly becomes quite a nice, clean blue flame. I guess the main point is there you can clearly see the annulus, that ring-shaped combustor in those upper images. This particular engine, we're not measuring thrust or anything like that, so there's no nozzle as compared to what you saw in the last image. This is just exhausting straight out. So it was one of the earlier tests.
So this is testing our safety and our control systems.
Right. How much data are you collecting during the process in this as well? You got sensors in there and...
I think we need that Macquarie data centre pretty soon.
Very good. Okay. Next slide.
So from here we move into... Yes, next slide, please.
Yes, sorry.
We move
and I'll play this, yeah?
Component, and I'll hand over to the University of Sydney.
Yeah, so at the University of Sydney, our contribution to this project has been on modelling the rotating detonation engine. The image you see here is what we call a numerical Schlieren. So it's showing the gradients of density. And you can very clearly see, and in fact, if you go to the next image, Chris, you can see it even in more detail. Yeah. You can very clearly see the structure of a detonation wave. So where we have the strongly black part of the image towards the right-hand side at the bottom, there's a vertical wave there. That's the detonation wave, and we get very sharp pressure rise and temperature rise across that. And then downstream, behind that wave, to the left of it, we can clearly see the transverse pressure waves, which move up and down the detonation wave on the back side of it. So in order to produce images like this is really a pretty picture, but it certainly shows us what the structure of the process looks like inside a rotating detonation engine. And we're using a method known as computational fluid dynamics, or CFD, which is an engineering approach to solve the governing equations of gas flow, or liquid flow, but in this case it's gas flow inside the engine, using computers and numerical methods. So the reason we need to take a computational fluid dynamics approach is that the governing equations for the transport of things like momentum and energy are very complex partial differential equations. And they can't be solved by hand or analytically. Instead, we have to obtain a numerical or a computational solution to those equations. But what it does is it provides us with very detailed information. Of course, it's a prediction, but it's a very detailed prediction of the processes happening inside the rotating detonation engine. So we can examine properties of the flow, and the next image shows a picture of temperature inside. This is now an annular rotating detonation engine. The previous images were flattened out straight.
Yeah.
This is showing the temperature. Okay, but we can also look at other things. But we can see here the high temperature regions, which are in the orange or red color, and then the low temperature regions, which are blue, where the fuel and the oxidizer enter the combustor. So we can look at this image or other things, and we can extract very detailed diagnostic information about what is happening inside an RDE, and look at things that are not possible to extract experimentally, because the conditions inside an RDE are very, very extreme, and only so many experimental data points can be extracted. So CFD, computational fluid dynamics, allows us to examine this in much more detail. And once it's been validated against the experimental data that is being produced, then we can use CFD for future optimization and improved designs.
What type of, and you've got I can't go back to your title, but what type of research and then the engineering is involved in this part? Because I imagine it's very multidisciplinary. How many researchers have you got on this?
So at the University of Sydney, working on this project, we have 3 academics. So myself, Ben Thornber and Dries Verstraete. So we specialise in slightly different things. And then we have a postdoctoral researcher, Sebastian Galindo Lopez, and 2 postgraduate students.
Right. And is there international collaboration in this? This is a highly specialised field. Are you collaborating internationally as well?
So at the moment, there's 17 researchers working on the project and 3 PhDs. Our international partner is Universität der Bundeswehr, which is a German research organisation which has close ties to DLR, and have brought in some expertise there as well. I'll talk about what Bundeswehr does.
Yeah, well, they're basically doing modelling as well and looking at the physics around the injection. So in this particular engine, one of the most difficult aspects is the injection and getting that working properly. If you don't get that right, then the engine won't work. So they're using a different type of CFD to what Matt just discussed there, more of an engineering approach, I guess, to quickly evaluate ideas and see how we can improve that injection.
Very good. And how much, other than its sort of application, is this research commercialised or potential for commercialisation in its own right, in terms of sort of rotating RDEs in their own right? Is this sort of groundbreaking research and what could be applied across sort of the RDE sector?
Yeah, look, 100%. The outcome of this is an engine, and as I mentioned before, an engine can be used for many things, and that engine will be a product in its own right. But its real value, its real utility will come when we integrate that into a flight system, and that's the next phase of work. And
how much, when I see figures like this particular sort of the CFD and the sort of the mapping being done, how much machine learning is involved in this, and sort of the advanced computational processing to learn from this and recognise what is actually happening? I imagine there's some advances being made there as well.
Sure. So far we haven't used any machine learning for this. It's all computational fluid dynamics. What you do is you take your physical geometry, which is the annular combustor, and you break it up into a mesh containing millions and millions of points, and you solve the equations of motion on those points. And we use supercomputing facilities to solve this. So we divide the domain up into subdomains, and each one of those is solved on a different processor. And then there is communication between the processors for the transport of information, momentum and energy and so on. So these particular simulations, depending on the resolution of the grid, but they can cost up to a million CPU hours or more.
Wow, nice.
Machine learning would allow us, I suppose it would come in another phase, would allow us to perhaps reduce the demand on the resolution, and the information at the smaller scales, which we are not resolving now, could be approximated based on a training phase that has produced data that can be accessed in the simulation phase.
Okay, well look, it's a fascinating area, and I'm a layperson in this in terms of sort of the advanced sort of technology being used. What's the project sort of life cycle, the research? Is there a sort of a project life cycle on this, and where you would expect it to be applied?
Yeah, so the funding for this particular phase finishes at the end of this year, and by the end of this year, we expect that the engine will be running for extended periods of time once the active cooling system is operational, and we're now looking at our opportunities for follow-on funding, both through the Department of Industry as well as the Department of Defence.
Great. Well, I suppose let's finish it off with a call to action. Is there a specific call to action? You want some market awareness around this, as you say, but yeah, what would be your sort of final message, and what would you like to see?
My final message is that there is a lot of good science happening in Australia, but we're failing to commercialise that good science and to keep a sovereign capability. Everything here is about sovereign capability. There's no point developing things to sell it off to the Americans or the Chinese or whoever else is the highest bidder. You know, if we can't retain talent in Australia, if we can't convert people from their PhDs and give them a job to move into, if we can't continue to fund good research that leads into new breakthroughs, then we're wasting our time. And this is a good opportunity where the Department of Industry has provided a mechanism to give us the opportunity to put meat behind that story, to actually put our best foot forward, to create a project, to deliver a commercial outcome, and see that all the way through to commercial success, so that we can take the money that's raised from that, reinvest it back into the fundamental research, and keep that cycle of innovation running.
I think that's important, obviously, from RMIT and the University of Sydney. you're doing some advanced research, and it keeps your researchers here, right? You're doing something interesting enough to keep them here.
Absolutely.
Yep, that's right.
Just maybe one final message from the University of Sydney. How does this fit in? Because we looked at the sort of the semiconductors, and again, maybe just talk us through the school. You're head of school in terms of research. What's your scale at the moment in terms of your researchers across the school?
Yeah, so we've got the aerospace, mechanical, and mechatronic engineering, and we have various sort of subgroups within that. So we have the mechatronics, which is robotics, and we have the Australian Centre for Field Robotics. So they're looking at automation and robotic applications in things as like agriculture, driverless cars, and robotic surgery. And then we have the aerospace department. So traditional aeronautical engineering, but also space engineering. And then in mechanical engineering, we have the traditional mechanical engineering disciplines. I'm from the combustion group within mechanical engineering, but we also have advanced materials design and a few other smaller areas.
Yeah, and RMIT.
Sorry, what's the question?
Just the size of your school in terms of the research and the number of researchers you've got in this space, but not just in sort of space-related fields, but advanced technology.
Well, in the propulsion field, we're actually a really small group. Right. There's only a couple of us. RMIT is really well known for materials work, and they do that with the DST quite a lot. There's the mechanical area, automotive, and advanced manufacturing. So we have one of the largest advanced manufacturing precincts in Australia for additive manufacturing specifically. So I'd say definitely advanced manufacturing and materials is our biggest area, and hopefully soon propulsion.
And what RMIT is, they've been with us on every CRC feed that we've done to date. They've been a very hands-on, practical university. And you do run the risk sometimes of being research for research's sake. So that practical aspects of what we found at RMIT and the applied aspects of what we found at University of Sydney, to be able to take that deep knowledge and apply it to a real-world problem is where the value's been.
Well, look, maybe it's just the people who we speak to, but I'm always seeing that strong link between academics and industry coming together now. That seems to be a major drive, certainly over the last sort of 5 years, but even up to the last sort of 2 to 3 years. And I think the government's innovation sort of growth centres across different industries has also helped, and they've pumped a bit of money. So it's always good to see. And thank you very much for your time as well and explaining this fascinating research. And hopefully we'll look up one day and see an RDE flying overhead. That's the idea, I suppose. So look, on that note, and we're going to finish right on time today, we've just been joined by Travis Reddy, the CEO for DefendTex, Dr. Adrian Pudsey, and Project Technical Lead at RMIT University, and Associate Professor Matthew Cleary, Deputy Head Research of the School of Aerospace, Mechanical and Mechatronic. Sorry, I was reading it wrong before, engineering at the University of Sydney. Gents, thank you so much for your time. It is linked on our Space and Defence chapter, and I'll put that in the show notes as well in terms of if you want to read more and reach out to these gents. So thank you very much for your time. I'll put you backstage.
Thank you. Thanks, Chris.
Thank you, Chris.
Thank you.